So we are going to continue our detour into the proof or disproof of fifth postulate, which comes under the rubric of what we call studying fifth postulate. And which is basically we are studying fifth postulate within the context of Euclidean geometry, and have shown that the fifth postulate, the validity of fifth postulate cannot be shown to it's shown to be it's shown to be inadequate, whether through a given point only one line can be drawn or not. So this is a sort of exercise which has historically exhausted the attempts of many people down centuries, and some have been failures towards in pointing these very things, in pointing whether the validity of fifth postulate is exists or not. So there have been attempts both ways, either to say whether a fifth postulate is a valid statement and it can be accommodated within the postulates of Euclidean geometry, or fifth postulate is inadequate. So the attempts in the later case have led to the just had led to formulation of non-Euclidean geometry, which has been significant not only in the history of mathematics but physics also, to say least about the importance of fifth postulate vis-a-vis in this context. So in the previous class, we just tried to show the attempts to show about fifth postulate. So in this class, what we are going to start with is there have been two attempts which have been shown to be further two proofs about this fifth postulate. So the first proof, which I'll just there's a proof called so we have to previously we tried to show the there might be some contradictions whether validity of fifth postulate can be accommodated within the other schemes of Euclidean geometry, but here we are trying to show the attempts which have been shown that fifth postulate can be accommodated within Euclidean geometry, the validity of that proof. And they have been termed attempts have been termed inadequate. For example, there is a proof called rotation proof. In rotation proof, what we are going to see is that, for example, so it was constructed by in 1775 to 1832 by this person called I'll just name him without I don't know how to pronounce him. So this is this Bernard Frederick Thibaut. So what the proof, the construction of proof goes like this. So if you take a line in a and you take another line like this, and from this you can construct a triangle. Now it's known as a rotation of triangle proof also. So if you have A, B, C are the different sides of the triangle, and now what we are going to do, we are going to rotate this triangle like this, first like this, then like this, like then this. So the first rotation will make the triangle. Then will make the triangle to so if you rotate, so it will come like this, then it will come like this, then it will come like So for each rotation, so for each rotation, for each rotation, so there can be different rotations. It can be either clockwise or it can be counterclockwise, whichever you would like to see the construct the rotation. And the rotation, so because once you can see if there's a triangle which is getting rotated, the sum of the rotations twice, it's as if it's rotating 360 degrees. If it's rotating, that means two right angles, two 180 degree angle. That means four right angles. So which is again you will reach to a quadrilateral. That's point. So what's the point? The point of the proof is like this. The point of the proof is like this. If in a triangle, A, B, C. So we'll have a triangle A, B, and C. And this is B. On this line you can say M. This is P. This is Q. This is L. This is C. So this is A. This is B. This is C. And this is N. So what we are going to do is that in a triangle, allow the side AB to rotate. Allow the side AB to rotate. To rotate about A. We'll rotate, allow the side AB to rotate about A, like this. Clockwise, until it coincides with CA. Until it coincides with CA, like this. So we allow it to rotate until it coincides with CA. Produce to L. Produce to L. Produce to L. So we'll produce it to L. Now let CL rotate. Now let CL rotate clockwise about C. CL rotate clockwise about C until it coincides BC. Until it coincides BC. Until it coincides. Now let CL rotate. So until it coincides. Now CL is going to rotate until it coincides with BC. So that's fine. Produced M. So first we are going to rotate this along this, then extend it along this line, then again rotate it. So you see there becomes a sort of two parallel lines. You can have sort of two parallel lines are there, which you can construct out of this construction. Finally, when BM has been rotated clockwise about B, BM has been rotated, BM has been rotated clockwise about B. BM has been rotated clockwise about B until it coincides AB. It coincides AB at M. It coincides AB at M. AB coinciding to M. AB coinciding to M. So that's fine. AB has undergone a complete rotation of, so that's what I'm saying. The AB has gone a complete rotation of four right angles. One right angle, two right angles, three right angles, and four right angles. So this construction, which I previously also stated, results in the rotation of four right angles, which is the sum of four quadrilaterals of a given four-sided figure. So the previous proof was also two parallel lines being intersected by two parallel lines, and the sum of interior angles cannot be greater or less than four right angles. So if it is, that would have led to contradictions. So it's also this rotation proof. It will lead to this thing. But now here there comes the catch. But the three angles of rotations are the three exterior angles of the triangle. So three angles are the three exterior angles of the triangle. So this is also an exterior angle of a triangle. This is another exterior angle of a triangle. You can see this is an exterior angle of the triangle. This is exterior angle of the triangle, and the third one, which is also an exterior angle of the triangle, you can see it is like this. You can also see it like this. So the point is that so this means if the sum of angles of the four right angles is equivalent to it's equivalent to two right angles. So these interior angles, the sum of these interior angles should also be equivalent to two right angles, or sum of two interior angles of these two should be equivalent to four right angles. So which will these interior angles, the sum of these two interior angles formed by these triangles, which are constructed by these rotations along these triangles, it should be equivalent to. So it cannot be less than or greater than two right angles. So if it is four right angles, the interior angles should be equivalent to sum of two right angles, and another interior angle also should be sum of two right angles. But here in this proof, there is an implicit assumption. Not only we have rotations, but we have also translations. Translations are also involved, and we don't that's a hidden assumption of not only rotations are involved in the process, but translations are also involved. But may be true only in case of Euclidean geometry. For example, if we use the same argument for the case of spherical triangle, which is constructed of, so it's a normal triangle. So you can make the same triangle on a sphere, and you make a spherical triangle by the same construction of rotation and hidden assumption of translation. So the sum of angles of any such triangle will always be greater than two right angles. So it's not necessarily it will be two right angles. Two right angles. So it can be greater than two right angles. So this somehow the proof could be true for normal triangles constructed on plane surfaces, but if you take maybe spherical triangles which can be constructed on not entirely surfaces which are flat or Euclidean in that sense, it will have some constructions. So if you read some passages on the book, so Gauss has some arguments. For example, what Gauss pointed out that to be equivalent as of that if two straight lines intersect two given lines and make equal corresponding angles with one of them, they must also make equal corresponding with other also. But this will be recognized as essentially proposition to be proved. So it's a proof in weighting. This proof in weighting that if equal angles, if two straight lines intersect two given lines and make equal corresponding angles with one of them, they should also make equal correspondings with the other line. So this is an implicit thing, and it assumes a prior assumption which has to be proved. So in that context, so this proof can be seen as an attempt in trying to validate Euclidean proof. Now there is another other attempt in this direction is a comparison of infinite areas. So it's a bit this one is second one is a bit more convoluted in the sense that I'll just try to this assumption of this meaning that if it the equality assumption, if corresponding angles are made by lines having equal angles and then the corresponding angles subsequent to them should also be equal. So this equality thing is also very much assumed here in the proof of this very thing. For example, and I'll just the proof was given by Louis Bertrand in the year 1731 to 1812. So what is the proof? So I'll just see first. I'll try to make we make a line proving the fifth postulate directly. The essence of argument is like this. Essence of argument is like this. So if it's A, this is B, and this is Pn. This is An. So this is A1, B1. You can see it. This is so you can have a parallel construction A2, B2, and A3, B3, so on and till we have An. And you can have one another construction which is you can see it like this. So now what is the argument of the argument is like this. The argument of the construction is that given two lines given two lines AP1 and AB1 cut by transversal A1 in such way. So given two lines AP1, now we can have two lines which are being constructed from this point A. So this is AP1, AP2, so AP3. So if we have constructed parallel lines here, so given two lines AP1, and A1, B1, so we are constructing two lines, one is AP1 and A1, B1. Cut by traversal. So you can see, so it's being cut. So if AP1 is one line and A1, B1 is another line, and so there's a traversal line which is cut. Just like in normal, if you two lines, they are being cut by the one line. So you don't assume that whether two lines are parallel or not. So because if two lines are parallel, they are being cut by a third line. So we assume here two lines are being cut by third line without saying that whether this line and this line is parallel or not. So if you start with this thing. So give two lines AP1 and A1, B1, cut by traversal A1 in such a way that the sum of angles P1 A1 and A1 B1 is less than two right angles. So P1A, P1A, this angle P1A1 and A1 and B1. So this angle P1A1. So you can see this angle this angle plus this angle, so is less than 2 right angles. So you can see it's implicit. Normally if they would have been exactly parallel, the sum of two, if two parallel lines for example are if this line and this line would have been exactly parallel, then the two angles, maybe this angle and this angle, maybe this angle and this angle, they would have been 180 degree. But from your implicit assumption that from usual perception, usual way of analyzing, so it doesn't seem to be parallel. So if it's not parallel, so this angle plus this angle plus this angle is less than two right angles. So fine. So it is to be proved that AP1 and B1 meet if sufficiently produced. So from this you can indirectly infer that if they are not if they are less than two right angles, so this means this AP1 A1 P1 and A1 B1 should meet if sufficiently extended to. So then AP1 will lie in the angle B1 TT. So construct AB so that BA. Now what we are going to do? So we construct AB. Construct AB so that BA1. So that BA1. So that BA1 is equivalent to. So B1A A2. So again, now what we are going to. So from this, if this and this are produced sufficiently, they are going to meet. So now if we can construct a line BA which is parallel to this line B1A1, so what does it mean? It means that we can construct BA1 is equivalent to B1A1 A2. So we can construct it this way. So if it's not, if you can construct an exactly parallel line from this, so this angle can be equivalent to this angle. So if it is that way, then where A2 is a point on A1, so where A2 is a point, so we can extend the constructions produced to A1. So you can make similarly constructed lines which are parallel to this line, and those subsequent angles can be made equal from this construction. Means we can construct, from this construction you can have for example so AP2, this is A, so you can have AP2, AP3, so on and so on, so that the angles P1A, P2, P2A, P3, so on and so forth, PAN minus A, PAN, are equal to angle BA, P1. Then AP1 will lie within the construct AP2 also that angle are equal to angle BA P1. Construct AP2, AP3. So that the angles PA1, P2, PA1, P2. So now what we are going to do, we are going to again make one was this parallel line. The other is that we are going to make a construction we are making P1A B. This was one. So one construction was we made this line parallel to this line such that this angle is equal to this angle. So from which you can infer that the lines are parallel. In the previous one was that this was not exactly parallel, and that's why they could this line and this line could somehow meet. Now we are going to make another construction from this point. We have drawn P1, we can draw P2, P3, P4 and so on, and ultimately to Pn such that they are equiangular angles from this construction. The AP1 to AP3, P1A, P2, P2A, P3, so on, P1, and the last one is this. So you can make consecutive or successive constructions of equiangles, which are angle to which are basically equal to this very angle, the angle from which we start. So now the point is this. So this is the integral multiple of angle BA1 can be found which can exceed BAA1. So you can say that we can find integral number of angles such that it will exceed this BAA1. So from this construction we can make n equiangles such that we can find a construction such that n can be chosen which exceeds this angle BAAN. So if it's that way, so it's not bit clear how we can choose it. So let me just stop. Let me just wait. Just suspend this thing. The multiple angle it can exceed and can choose a lower such that A1 will fall below AA1, and an angle BAPN greater than BAA1. So if it can be such that it can be done in a way such that this will fall and can be such that APN will fall below AAN. So APN. So if you construct, so if these are equiangular angles such that these angles can be constructed such a way they are equiangular, but if the choice of angles is n, we can make the addition of these equiangular angles such that this will somehow fall this thing. So we can construct a line Pn, so such that this will be subservient or it will come under subservient to this thing, or this BAN should fall under BAPN. So if it is that way, so what would we get? So I just quote him. So if this means that since the infinite sectors BAP1, P1A, P2, Pn minus 1A, Pn can be superposed, they have equal areas and each has an equal area to the inner sector. So each has an equal area equal to the inner sector BAPN. So there are infinite sectors like BAP1, P1A, P2, P1A, P3. So many sectors you are constructed, and at the end the last sector may be Pn minus 1 and Pn. So what? But they can be equal sectors. So the infinite sector can be BAPN. This can be divided. This BAPN, the last one, of which all of them are subsets, from which you can get these sectors. It can be equally divided by n. So n equiangle sectors, equal sectors. So fine. Next, on A1 proofs we have A1, A2. So we can have A1, A2, A2, A3. So on, we can have A1A, A1, A2, A2, A3, so on, AN and AN minus 1 and AN. This is fine. Then the infinite strips BAA1, the infinite strips BAA1, B1, this, B1A, 2B2, this, and B2, A2, A3, and Bn, and so on and so forth, or superposed, they have equal areas, each equal area divided by sum. So from this you can have this argumentation. So if we can construct this equispace, so we can have this sort of a parallelogram, or so from this, so we can have this things figure, then this figure, then this figure, then this figure, and then to AN. So if I just like a sort of a quadrilateral, which might be equiangular quadrilateral. You can say it like this. So BA1, B1, B1A, B2, A2, B2, Bn minus 1, An, Bn can be superposed and thus have equal areas, each equal to the area of the infinite strip Ban divided by n. So since the infinite sector BAPN includes the infinite strip BAN, it follows that area of the sector BAP1 is greater than the strip BA1 is greater than, so BAP1 is greater than BAP1 is greater than BAA1 B1. So therefore AP1 must intersect A1 B1 if produced sufficiently for, so BAP1 is greater than the strip BAA1 B1 So what can you say is that so since this strip BAPN is greater than this strip, so this means this strip BAPN should include all these infinite strips BA1, P1, BA1, A2, B2, B2, A2, A3, BN. So BAPN as a strip should contain all of these infinitely equiangular strips, you can say it. So this means that from this, what we can say, so this means that therefore AP1 must intersect AP1. AP1 must intersect A1 B1 if sufficiently produced. So from this indirect construction, we can say that AP1 must, the starting assumption which I started with, that AP1, which we had assumed that must intersect A1 B1. So because because it lies in this thing, so because it lies in BAPN, so that's it. But this construction again shown to be fallacious in that sense that, for example, we are treating infinite magnitudes as if they are finite. So they are finite. So again, for example, weakness of the force proof is that BAAN and B1AAN so we can compare these two signs. So from this, so these were attempts in what I would say, the way we have reductio absurdism, we have attempts which are fallible attempts to prove the validity of the fifth postulates historically from these two, this rotation proof and this proof which was designed that way in order to show that the process of showing that parallel only through one point parallel lines, you have only one point through which two only one point is required. You can only draw one from a given point. Only one line can be drawn, which is parallel to a given line, which is also called fifth postulate. Now, if you read the section third of this unit 3, so it's a very interesting unit. There are very good personal anecdotes of various mathematicians, Gauss, Wallis. Well, so they are well documented here. A sort of with a sort of very interesting stories which you might have time, you can go through them. The only point to mention here is that in the history of discovery of non-Euclidean geometry, the Kant's point of view of space, which was that they are a priori notions. If you study in greater detail this critique of pure reason, maybe there that he uses the term transcendental. Those space and times are a priori constructs, means they have been existing since and they are going to exist again. So if you have, so when we relate geometrical constructs with some notions of empirical world, so these are all constructions subject to the experience, subject to the experimentation. So when you read the attempts in trying to prove or disprove this fifth postulate, or even in the early attempts of non-Euclidean geometry, so you can say the space as an a priori construction was somehow replaced by a notion of geometry where the construction is somehow experiential. It's how we experience things. So there have been attempts that way. So you can read these statements. So now to emphasize this thing, so there have been mathematicians like Gauss, Bolyai, I don't know how to construct them. So maybe this will somehow nails down this diagram. Somehow it clears it very much. For example, this is attempt by Bolyai. So if you have a line, so you can say it, this line. So this line, there is a perpendicular to the line. So you can have this, you can have this. So you can see it. So if you don't assume that they are on a plane, so if it's a space, it's like space. So you can construct a line. Normally, it seems on a simple board they are going to somehow meet, or they are going to meet. No, if you see it like this, space, open space. So from this you can construct a point like this, which is parallel to, which will never meet this line. Or you can construct this line from this point, it will never meet this line. Without being prejudiced the fact that I'm using this thing on a board. On board it seems that they will meet. But if you see it from this vantage point of this point, so this point, and if you draw a line from this point, or you can draw infinite lines, which will not necessarily meet this line. And from this one of the line, you can have exactly a straight line which you can construct, which can be perpendicular to this line, which you normally call as parallel line. So you can have as many as lines which can be equally parallel. Parallel in the sense they will not meet this line. That's the point. So you can say that thing, this proof P, Q, C, D, E, F, A, B. So this is the figure I'm going to make. And so if, for example, infinite, so this is the point, you can see it. Separate the line. Since the rotation of PQ in either direction, there is no cutting line. These postulate line. So maybe so we can have that. So we can have this construction. So Lobachevsky argued that if one starts from PQ, and allows PQ to rotate about P in either direction, allows PQ. So if you start from PQ and allows PQ to rotate in either direction, it will continue to cut AB a while and then cease to cut it. So you can have an image. So Lobachevsky, so you can see it. If you allow it to rotate, so it will cut it, but sometimes it will not. It will cease to cut it. He was thus able to postulate the exact existence of two lines through P, which separate the lines which cut B, AB, from those which do not. Since the rotation of PQ in either direction, there is no last cutting line. These postulated lines must be first and the non-cutting lines. It will develop that two lines parallel to AB have properties quite different from the other lines P, which does not cut. So if you start, Lobachevsky's proof is like if you start from this point, which is perpendicular, and you rotate this line, and you will reach to a point, you will construct lines which may cut this line or which may not cut this line. The lines which may cut it may have different properties as compared to the lines which you are going to cut it. So which are later you can see it, how we construct different geometries. So there have been Gauss, Bolyai, and Lobachevsky, a Russian mathematician. Bolyai, and there have been two Bolyais, his father maybe. And maybe smaller names, maybe they might have some contributions. So I don't know how to pronounce them. You can read the book. So these are the things. And maybe this one important point in the history of non-Euclidean geometry is apart from maybe these people, there have been Lie, there have been Beltrami and Helmholtz. Maybe if you read, there's a famous essay of Helmholtz on origin and significance of geometrical axioms. So his arguments were from optics and physiology. And maybe the point of mentioning of Riemann is because the clinching argument of Riemann was basically to qualify this understanding that the understanding of space and the understanding of this Euclidean space, which is constructed of n dimensions, you can relate it with some physical space. And if I use the exact words, what he's saying is that for example, the words is he uses the word hence flows as necessary consequences. Uses the words called different major relations, and the notions of magnitude, general notions of magnitude. So the three-dimensional space, which we also called Euclidean space, we can call it as a triply extended magnitude or infinitely extended magnitude. Now it is triply extended magnitude is called Euclidean space or Cartesian space, where we read three numbers. So you can have n-dimensional space, you can have three-dimensional space, 4. So it's our construction basically. It's not a priori, and the construction can be warranted by reasons for geometers or for logicians or physicists, or so there can be different reasons we can invoke for those very constructions. So maybe the point of Riemann is here, how he and these extended can be deduced from experience. So this is deduced from experience. So this is the important point which I want to emphasize, or which Riemann wants to emphasize, and again I'm re-emphasizing in this lecture. So, and at the end, so if you just, it was, for example, maybe in the history of non-Euclidean geometry, if you see Felix Klein he has written maybe those volumes. So when working on this thing, whether the lines are not parallel, or you can construct more than one line which can be parallel to a given line, and the properties of those lines which cut them. So you can have different geometries of the name you might have heard: hyperbolic, elliptic, parabolic, or the terminology which has been imposed since. So to only mention, for example, the definitions how straight lines can be constructed. For example, so straight line can be constructed as infinitely two distinct points. Two distinct points. Under the hypothesis of acute angle. None other than so a straight line be constructed from infinitely two distant points, and straight line can be constructed none other than hypothesis of acute angle. So this is also known as hypothesis of acute angle. So if maybe they will infinite two distant points, they straight line can be constructed from them. Under obtuse angle, it's none. And only one under the hypothesis of right angle. So if there's a right angle. So there is one. So there is two, there is none, there is only one hypothesis. But here it's right angle, obtuse angle, acute angle. Straight line contains two. In the first case, the straight line contains two infinitely distant points under the hypothesis of acute angle. This is first case. None under the hypothesis of obtuse angle, and the third one is this thing. And there have been other scrutinies. If you want to derive the axioms of geometry, if you axiomatize the axioms of geometry from the point of view of logic, then maybe Hilbert, Peano, and Russell, and Whitehead, and they have attempted those exercises. And we have done the attempts by Hilbert to logicize or axiomatize these geometrical, our study of geometry. So those attempts have been constructions. Apart from these things, how we can construct hyperbolic, elliptical, or parabolic geometry. So in the next classes, we are going to just further develop on or further construct these constructions like hyperbolic geometry, elliptic geometry, and other geometries, elliptic plane, which might resemble Euclidean geometry in certain limited cases, and there can be some deviations also, subtler deviations. And those constructions are not only helpful in mathematics, but physics also. So I'll stop here.